Class, good to be with you again. This is Whitlock and Schluter, Chapter 12. We've covered the paired and independent scenario, how they come up. We've looked at the paired t-test and confidence interval. Now we're going to consider the independent t-test and confidence interval in this example. We've got Whitlock and Schluter, page 287. And we're talking about, we called them horny toads when I grew up in Nevada. These guys were out in the desert, and sometimes me and my buddies would go out shooting them. So there's a hypothesis here. We've got 30 of these guys that have been killed by shrikes, and they're wondering if their horns are a little bit shorter, and so they're not able to defend themselves as well as the longer horned ones. So they found 154 living ones, and we're going to do a test to see if the difference between those two groups looks like inside the population. So let's do mean for the dead versus the living ones. And this is not just any dead, but these are those that were killed by shrikes. Living. So is there a difference in horn length between the two? We're going to do a sample from both and make an inference to the population. If the difference in the sample means is large enough, then we'll go, yeah, we think there's a difference. Okay, so first off, we're going to do it from a confidence interval perspective. So in the confidence interval, we're interested in x bar, and let's just put living minus dead instead of dead minus living. It's arbitrary which one you do. It does not make a mathematical difference. I like to do the positives, or the larger first, just because I work with positive numbers. Okay, so that's a difference of 2.29. Now, here's the most complicated part of the whole calculation. We need to do a thing called pooled variance. And the reason we do a pooled variance is because we're assuming that the two populations have the same variance. So I'm just going to put that. We not only have a mean, but we have a variance here. Okay, we're not attempting to. We are going to estimate it, but we're not trying to make a claim about this. We're simply going to assume that sigma squared dead equals sigma squared living. Okay. Now, if we do not assume this, then the test becomes slightly different, and that's called a Welch t-test when you do the t-test. And you could have a Welch confidence interval as well. The book treats it separately, as it should, and I'm going to go ahead and skip that one because I think one is enough. But it does give us a third case. And so the way we work it here is assuming that the pooled variance here, I want to just note to us that s squared, sample standard deviation squared, is the sum of xi minus x bar all squared, right? Divided by n minus 1. Awesome. So what that means is I can multiply both sides by n minus 1, and I get n minus 1 times s squared is the sum of the squares. And so that's where the pooled formula is going to come from. So the pooled formula then takes the n minus 1, so I'm just going to put that n1 minus 1, but then it throws the variance on there. Okay. Plus, we need the sum of the squares for the other group. That's the first group. So now we're going to do n2 minus 1 times s2 squared. Now I have the sum of all the squares, and then we have to divide by the appropriate degrees of freedom, which is going to be n1 minus 1 plus n2 minus 1. And so it's commonly written n1 plus n2 minus 2. Okay, that's the pooled variance. As you can see, it combines all of the data together. It increases our power. That is how sensitive the test is to detect the difference. So the standard error then goes like this. Let's see here. We got the pooled, good. So we're going to go sigma squared pool over n1 plus, oh, and I shouldn't say sigma, that's population. If we had that, it'd be great, but we're estimating. Sigma squared pool over n2, and then we take the square root to get rid of the square. Now, plugging in is not too bad, as long as we're given those variances, which we need to plug in here first. So variance on the first one, we got 154 sample. Variance was 2.63 plus, I'm going to go ahead and clear this out just to make space for myself. Hopefully you have more room. Plus, I had a 30 minus 1, and the variance in the second group there was 2, or standard deviation was 2.71. We square it. Now we divide by 154 plus the 30 minus 2, and that gives 6.98. Okay, so 6.98 over the 154 plus 6.98 over the 30. Now you could simplify that by factoring out, and that's fine. I like this format because it's intuitively like you did before, but you can see there's an addition of variances. And that gives us 0.527. Okay, so let's see, looking for space here. We'll do the diagram. Okay, we're going to put the difference of 2.29, that is in millimeters now. That's an x bar 1 minus an x bar 2, as opposed to an x bar difference from the paired case. And then we'll do a t level. So on the t level here, that's a 0. Looking for the e. So e again, we're going to have to look up a t. So let's see here. T. T's 0.052 degrees of freedom. We need a new one. Okay, so the degrees of freedom for this case, let me put it up a little bit higher. I didn't talk about the assumptions. Basically, in the assumptions, we basically need both N1 and N2 to be random and normally distributed. If I have that, then we're good to go. The degrees of freedom then is going to be N1 plus N2 minus 2, as you may have guessed from the denominator of the standard error. Okay, so in our case we have 154 plus 30, that's 184 minus 2 is 182. So we'll go ahead and check our table, and there's 2 of them here. I've got a 180. That's close enough. It goes to 1.97. And just for eyeball's sake, this is a good time to notice. If you go up larger, up at 1,000, it's 1.96. That's the number for the normal distribution. So we're seeing the t distribution is approaching the normal. Okay, times standard error. So that t-score was 1.97. Standard error was 0.527. That's going to give me an E of 1.04. So my margin of error is roughly 1. We add and subtract here. That's going to take me up to 3.43. And we'll subtract. That's going to be 1.25. Okay, so we're 95% confident that the difference is 1.25 to 3.43 millimeters. And that's a real difference. It doesn't include 0 because the left side is not negative. So looks like the researchers are right. These living ones do have longer horns. Now, in passing, I want to just point out to that, what's the rate of horn growth? If these guys have been alive and their horns are still growing, then they ought to have slightly longer horns, shouldn't they? So does this just prove the difference here? Well, it gives evidence along the lines of the researchers, but there's still something else going on. So I'm not saying this was bad or poorly done, but we want to take it just for what it is. And strictly speaking, you see this limitation on it. How much time has elapsed to possibly confound the observed difference with the living due to better fitness or living longer and just having it grow out because they happen to be the ones that didn't get picked. Okay, so that's something to think about. Now, let's go ahead and put this into the hypothesis testing context. Same scenario, we're going to use a 1% level of significance though. And so here we go. The null hypothesis for this one, of course there's no difference, so we just depict that like mean living minus mean dead. Okay, and just by way of review, mu looks like a U, but there's a long leg on it. Okay, that's mu. So the alternative hypothesis, mean living, the difference equals 0. Why do we do equals 0? Why do we not write mean living equals mean dead? Well, for one, you could. That would be fine. But the reason is there's two different groups, and for testing purposes, we only have one statistic. So we pull a clever trick and we do a subtraction in this form, and therefore in the statistic, x bar 1 or living minus x bar dead equals 2.29. We already did that in the previous one. Now I have a single statistic with a single distribution. So we can run this thing. That's the whole trick. And we had a discussion of this in the confidence intervals as well. So mean living minus mean dead not equal to 0. Okay. Now I've got my pooled variance, my standard error calculated. So the test statistic here, it's our usual guy. We'll go ahead and do the stat minus the parameter all over the standard error. And so the stat is 2.29. Parameter is a big 0. You won't even see it written in the book formula, but this makes it easier to remember and conceptualize. Okay, so 2.29 divided by this 0.5, I get 4.35. So the null distribution has center 0 on the x bar living minus x bar dead scale. The actual difference was 2.29. The t-score level was 4.35. And so how do we do? Well, again, we can find out in one of two ways. We can look at the t statistics. So we're going to compare that t, 4.35, versus we already found the critical value, which is 1.97 from the previous confidence interval part, and this is greater than. Okay, so when our t stat, absolute value t, is greater than our t, And you know what? I have to take that back. 1.97 is not the right number because we're using a 1%, aren't we? So we better go. 1% is this column, third from the right. Around 180, we're at 2.6. So it's not 1.97, it's 2.60. So that's T.012. That implies still, if I go in, that 2.6 somewhere here. That's 1%. This is 0.01, and I'm putting a 2 on there indicating it's a two-tail. So there's some on the left, but that is the 0.01, and it cuts us off at 2.6, clearly in the tail rejection region. So reject the null hypothesis. P-value, we'll have to look at the software on it. So let's go ahead and do that. Again, before we analyze the data, we always want to look at the descriptive statistics. So for the horned lizards, the structure looks like this. I've got this squamosal.horn.length, and then survive. Let's see what is going on with that. There's a 1 all the way up through. The 1 turns into a 0 here at 155. The 1 is representing the living, the 0 is representing the dead, and the horn length is all in one column. This is our standard case variable format. So I have the two variables, length and survive, and then these are all the cases or the individual observations. So in the box plot command, again, I'm going to look at my text examples file. We're in example 3 here. So let's go down to that one. We will attach the data and do a box plot. Also a good idea to get the statistics out. So let me do the box plot lacks the labeling, so I want to put the labels on with the names argument and the main argument for the title. See that those add them on, dead versus living. Clearly the living have a larger horn length, but there's some overlap, so how's it going? Here's the technique to separate the horn lengths of the survivors. The double equal sign is illogical, so this will give me only horn lengths of the survivors, and then x2 horn lengths of those dead. I'm going to run that whole thing, and doing a summary gives me all the stats I want except standard deviation, so I'm doing that command separately. Semicolon separates the two commands so I can put them on one line and have them both run. Is there a statistically significant difference? Let's do the confidence interval and test to find out. So to look at this from our studio to get that p-value, I want to go ahead and just do pt. We had 4.35 and degrees of freedom was 182. Go ahead and hit it one time. Ooh, I got a 0.999. That's because that's the value I get left tail region. That's always the output of the RStudio, and you clearly know that by observation. So if I go 1 minus that number, then there's what I'm looking at. Since it's a two-tailed test, we'll go ahead and multiply by 2, and we've got it. 2.26 times 10 to the negative 5 power. So we can go ahead and put 0.00002. Very strong reject H null, and we already had a discussion of what that looks like. One last note, at this time, the horned lizard data on R does not match the data in the book, so I'm not going to do that one on R. Okay, I'd like to show how to do this on RStudio. So we had that box plot up. Now let's go ahead. I've got some scripts here that directly do the calculations. That's worth taking a look at, because if you have a similar example, you can just define x1 and x2 as whatever the variables are. This script will give you the results. I want to focus in on using the t.test command. I have var.equal set to true. That is the default, but let's leave it as it is. I've got the two groups, x1 and x2, that I've formed. So I'm going to go ahead and run this line first. I get my two-sample t-test, 4.38. This varies from our result simply due to round-off error in the data. So we did get the same exact methodology here. Here's our confidence interval and a p-value that we obtained, degrees of freedom. I'd like to also bring attention to this form of syntax. It will actually be most common for us. It uses the horn length by survive. So if you look at the original data structure over here, lost that guy. We have horn length and survive. All the lengths in one column, a label as to whether, a categorical variable as to whether or not they're in the survive group in the other column. So all the horn lengths are going to be grouped by the survive. And again, equal variance. If you put false, that will give us the so-called Welch t-test, not assuming equal variances. But if I run this one, boom, you'll notice this is the exact same result as the previous line, but a different call to it.